Hello, welcome to my first draft video. This is just going to be a casual conversation that I'm kind of having with myself to you. My name is Khalees Edson. I'm in Math 32 for the summer of 2021. Yeah, 2021. And yeah, let me just jump right into it. So my topic's Brownian Motion. Really glad I ended up with this topic. I really wasn't sure about the others. I saw this one, looked at it real quick and was like, oh, this has something to do with chemistry. Sorry, I'm left-handed, by the way. I smear my ink everywhere. Wow, though, this was a lot. And if I wasn't so interested in chemistry, I don't think I would have been able to really like dive into the research that was needed to understand this. Wow, all I can say is this is actually a super important motion, a super important topic. I am blown away that I didn't know this and I wasn't taught about this. So Brownian motion, just to give you like Wikipedia, if you looked it up, didn't know what someone mentioned it, you're like, what the heck? It's just the random motion of particles suspended in a medium. You're like, that's a lot. It's a lot. So random motion of particles suspended in a medium. So we'll start with medium. Medium is usually like a liquid or a gas of some sort. And by particles, let's go with a glass of water with pollen in it. And it's just, Brownian motion is just that pollen piece moving around in the water. What's crazy is it is random, but Brownian motion is the calculation of the random particle moving. So Brownian motion was actually named after Robert Brown, who discovered Brownian motion on accident. So that little example I gave you with the pollen in the water, he actually did that. He was a biologist. I don't know why they named this after him per se, but whatever. He was doing another experiment. I can't remember what it was off the top of my head. He put pollen in water and he thought it would just settle to the ground or just stay suspended in one spot. And he saw that it was kind of wiggling and moving around, floating down and bouncing back up, slightly. And he was like, oh my gosh, pollen is alive. And dove into this whole other thing about trying to prove that, pollen's a living thing. He was wrong, but he actually, started kickstarting the movement for chemistry itself. So this motion, along with a lot of Einstein's work and Avogadro's number and a couple other mathematical equations, is what chemistry is. It's the study of the molecules and what things are made of. This helped prove that atoms were real and the micro scale was real, and that we could study molecules and atoms and their movement. There's nothing even on this computer screen. I don't even know why I'm trying to look over there. So Einstein's stuff is actually his relativity theory, which he spent a lot of effort on. He won a Nobel Prize for a couple of these things. And a lot of it came from what he did is he used Taylor series and a couple other calculus stuff to create some kind of like basic equation in tracking. So the main problem that he had with it is he didn't have the best technology actually to do this, which is crazy to me that he even could come up with any of this stuff and like prove the existence of molecules and atoms. The calculations that you have to do for Brownian movement, so essentially is you're not going to ever see stuff calculated for more than a couple seconds. The reason of this is because it is such a micro scale that you're tracking a molecule that's moving around and hitting other molecules that you can't see with your physical eye. There are about 10 to the 14 billion collisions in 2 seconds. That is a lot to track. So a lot of these numbers and things I'm going to have on my graphs, it's going to be 0.2 seconds, 0.5 seconds, 0.7 seconds, 1 second, and then 2 seconds. Something else I want to include with the video, I should explain that. My video is going to be a presentation with the history. There's a lot of different things that I need to mention, talk about towards Brownian motion to get the better picture of it. And then I want to jump into I want to show a simulation. There's a lot of cool simulations. There's one called Random Walk that I've been looking at and trying to use. And Random Walk is Brownian motion in a simulation. It's essentially, they use the calculations and the probability stuff I'm going to be talking about, and just, you're just going to pick a molecule or a thing, and it's just going to be in a simulated box, and it's just going to move around, and you're going to be able to see, track it and see how it goes. I also want to show dye moving around in water, because that's a really cool way to see how fast and random the molecule spreads throughout. And then I also want to include some coding. I'm not the best at it, but I'm really trying to get a graph created. And it's going to pretty much look like a bell curve, and then a bell curve just slowly dropping until it flattens out. And that's just the rate of the randomization of the collisions over time, which is really interesting. But yeah, and then I kind of want to, after all that, I only have 5 to 10 minutes, so I'm really going to cram it in there. And then after that, I want to just have some kind of open-ended questions, just to get I feel like it's important to tie in real world problems and aspects into anything. So, you don't get those questions, well, why would I ever need this? What would I ever use this for? I was that annoying ass student, sorry, that would be I'd be in math class, why would I, what am I ever going to use this for? And, I actually needed a lot. I needed a lot of it. But I want to just tie in just questions. For example, Brownian motion has a lot to do with calcium in the bones. There's Brownian motion on climate change and pollution, tracking how fast a particle or smog, because a medium is liquid or gas, so in a certain volume, how fast a particle moves and spreads. So you can track that, or you could pick a room and the rate of which, say dirt particles, spread and settle in the room. A lot of cool things too that people don't realize is, this also is, oh my gosh, what is it called? I think I actually have it over here. This has to do with astronomy as well, stellar dynamics. So this motion is also these calculations that Einstein came up with, many, many, many moons ago, are still being used today for deep space. What they do is they track black holes and stars and other things that move with gravitational forces and how it impacts them. That random probability of how they move around in literal empty space, or not empty space, is it? I don't know. That's a whole other thing. And yeah, so I'm definitely going to turn in a paper. I don't know how I'm going to turn this in, or where I'll turn it. I guess I'll turn it into you somewhere. I want to turn in a paper of all my research and findings. Like I said, this is pretty dense. There's quite a lot. I mean, this is on a lot of work of Einstein's, and it's been incredibly, it's a lot. It's been incredibly difficult for me to, I've been reading this stuff over and over and over and over. I've been talking about it constantly just because I want a way to present it. I've been telling a lot of my friends, and defining it for them. And, a lot of them their majors have nothing to do with STEM. So this kind of just goes over their head, and a couple of them I've been able to help them understand it, which is gonna help me be able to teach it a little better, just so I have groundwork. I think I'll talk about Robert Brown later. I really don't know why they named it after Robert Brown. He did find it by accident. Oh, he did help chemistry itself, but yeah. And this motion also has to do with thermodynamics and kinetics. So, I mean, heat and energy is a huge tie into this one. Gravity is usually a force that's also included, just because, you know, most things, gravity is pushing down, even in a liquid or water, moving it. But you do get the random probability of it hitting the molecule and going up, or, you know, whatever. I'm trying to think. So I just had like a few questions per se. In showing it, I kind of want to do, I don't know if this is completely Brownian motion, but like I want to do like homemade snow globes, and essentially they're just going to be like comparing two mediums and comparing different sizes, you know, because the bigger the molecule, the more objects it hits, you know, the more things it's colliding with, because the surface area is bigger. And then, you know, the more you heat up the water, the more the molecules in the water are going to get excited. You know, they're getting some energy in them, and they're just going to start moving a lot faster. And, you know, that's going to push the particle that you're looking at, and the probability and the calculations are going to be faster. Going to be a lot more collisions going on and different mapping. And so I just wondering if it's a good idea just to kind of show, you know, shake it up and see, oh, look how fast those particles move in the water. Look how fast those particles move in the oil. And then, you know, these are big glitter particles. These are small glitter particles. And you kind of see how they sink differently and move around. And the bigger ones tend to, you know, float down slower. And just because they are colliding with more things from below them. So it's interesting. I don't know if that's a good idea, or if it doesn't really tie into it. So I've been thinking about different things to show. And then, I mean, I feel like a big kicker at the end is going to be my question on, I have a sticky note here of it. Would this affect how greenhouse gases affect the atmosphere? So that's tying in with climate change. And then, should I do, for the calculation-based stuff, I was just going to present the calculations like Einstein. There's some, oh gosh, what is it? I mean, diffusion is in this. I've got geometric stuff. I've got thermal and thermodynamic equilibrium. Statistical mechanics are in this. I've got Raymond's sum. There's the whole astrophysics stuff in here. There's different models. And then Einstein's theory stuff, like I said, that one's a lot. And then if I should tie in like my own calculations, I guess I'm gonna have my own calculations. I'm gonna code my own like MATLAB graph. So I guess that kind of answers my question. But yeah, hopefully you somewhat enjoyed this video. Please let me know if you feel like I should add something else in, or, you know, if I need to go further, or like I'm not tying this in enough with like stats and probability, because this one's a little difficult just because it is random probability and the random calculations of where this molecule is going to hit and how exactly it hits and how fast it's moving, and then which direction it's going to go, and then the impact of all the forces. But yeah, I could go on and on about this. I've literally been talking about this thing nonstop for 4 weeks, 3 weeks. How long have we been doing this? 3 weeks. My friends are kind of sick of it. But yeah, thank you for tuning in. I hope maybe I taught you something. I hope I taught you something.